Okay, let's go to the third problem and let's calculate the rotational degree of symmetry there. We've got this illustration of something that looks a little like the sun, and we're going to make reference to this diagram next. And I think you're starting to get the idea of why we're doing this. This is a diagram that has, let's count them. We've got 1, 2, 3, 4, 5, 6, 7, 8 rays, evenly spaced, pointing around a center point. That means that we're taking our 360 degrees and we are dividing it equally into 8 spaces. And if you do the math, we end up finding out that the separation between each adjacent ray is 45 degrees. That means we've got 45 degrees here and 45 degrees in every space that we have adjacent between rays. So let's make that notation here. And now we're going to go ahead and we're going to take patty paper upon which we've got an illustration already drawn. I basically trace the illustration. Okay, we're going to line up this in such a way so that we've got the tips of the triangles aligned along the spokes of this wheel, and I'm going to tape the patty paper down. Okay, that's going to be our reference object. And now we're going to take a movable patty paper. Let me also be sure that we mark the starting points with red dots so we know where we started. And now we're going to go ahead and we're going to rotate this object around in reference to its original position. We're going to start with them overlapping like this. Okay, and we're going to just see, again, we've got to figure out what is the least angle that we can rotate where the figures will overlap. And that's going to be our degree rotation of symmetry. So let's start turning, 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 turning. Okay, are they overlapped yet? No. I think you can see the patty paper below shows they're not overlapped. And there. They overlap right at that spot. Okay, so now they are overlapped. If you'll notice, we move from a red point here to a red point here. That is moving 45 degrees. We have moved 45 degrees around the circle. So the answer to the problem is 45 degrees. That is the degree measure of symmetry. That is the smallest angle that we can turn and have the figure overlap itself. But let's go and let's finish counting the number of positions. So we'll also have the order of rotational symmetry. So this is the first position. I think you'll see pretty easily. This is the second position. This is the third position. This is the fourth position. This is the fifth position. I'll try to get my hand out of the way. This is the sixth position. This is the seventh position over here, like that, and the eighth position brings us back to starting point. Okay, so basically we have a rotational order of symmetry of 8. We said the degree symmetry was 45 degrees, so let's put down, yes, we'll put down 45 degrees, and the order of rotational symmetry is 8. And let's quickly look at the last one, because the last one is kind of easy. In this example, we're given an arrow, and we've got to figure out what is the least degree that we can turn the arrow so that it overlaps on itself. So I'm just going to tape the arrow down. I'm going to put a copy of it on top of it, and I'll pick a point that's sort of in the middle, and I'll start to rotate this arrow. And I think you're going to see that there's nothing you can do. The arrow's not overlapping itself. It's still not overlapping itself there. We got to go all the way around. Okay, and we said that the move or the rotation that brings it back to the original position is order 1. So we only have one order of symmetry here, which is another way of saying that the angle is 360 degrees. So there is no angle less than 360 degrees. The only angle here is 360 degrees. That is our rotational degree of symmetry, and our order of rotational symmetry for this object is just 1.